In this section, we will build up data structures to describe the state of a biological system. At any given time, you can think of a cell as being a complex data structure ultimately composed of atoms. There are changes in the state of these atoms in terms of their position constantly occurring that give rise to the behavior we call life. I want you to think of a cell as having two things: a physical representation in reality in the form of particles, and as a design abstraction in the form of a sequence object. We'll represent the sequence in the form of a nucleus and the physical atoms as a set of particles. A set in Java is like the group of students in a classroom. They are all unique and they often sit in different seats. There is no immediate motivation or method for ranking them, but the key point is that each person can only exist once within this collection of students. Things like this, in which all members are unique and they have no intended order, are called sets. In the case here, we have a set of particles, which basically will mean atoms, and that's it. There is nothing more going on in a cell. Those particles have a position, a velocity, and based on this species description, they have some identity that defines their behavior. The genetic composition of the cell is in essence already captured if we describe the full structure of interactions between atoms in this particle set. However, the emergent property of replication enables a novel abstraction to exist that is this simple idea of genetic composition described as a string of letters. Therefore, we will capture this useful abstraction as a separate data structure called the nucleus. Alright, at the most basic level we can discuss four classes of species: photons, atoms, molecules, and complexes. The photon is entirely defined by its wavelength, which is a simple real number expressed in nanometers. An atom is defined by its number of protons, neutrons, and electrons. Based on the number of protons, one can look up the name of the atom like carbon or sulfur, so we don't have to include both pieces of information. Num protons is sufficiently expressive. All these counts are integers because each particle is itself quantized. You can't have half an electron. A molecule is a structure representing a graph of atom objects connected by covalent bonds. Finally, a complex is a structure represented by a graph of molecules held together through non-covalent bonds. There are many ways of expressing this graph that is a molecule. Here we see 8 different but equivalent ways of expressing the structure of the chemical in aspirin pills. For visual consumption, you can draw an all-atom structure showing every bond and every atom in the molecule. These are cumbersome to look at and draw, so this representation is rarely used. Organic chemists will typically employ a condensed version of the all-atoms view by omitting all the hydrogens bonded to carbon. A ball and stick model captures a three-dimensional conformation of the atoms. It captures the structure, the lengths of the bonds, and their relative positioning. A space-filling model is like ball and stick, but it also captures the radius of each atom and thereby gives the viewer some notion of the surface shape of the molecule. For verbal communication, there is a formal rule-based nomenclature called IUPAC, but older common names persist. Because IUPAC names can get long and cumbersome, many people prefer to use the common names, particularly for biological molecules, which are quite large. For computer-readable serialization, the SMILES and INCHI formats capture the structure of the molecule as a short string. All these representations ultimately mean the same thing and are usually interconvertible. A graph is mathematically defined as an ordered pair of two sets. One of these two sets, V, is the set of nodes. For a molecule, each atom is a node. The other set is the set of edges, which is itself expressed as a set of ordered pairs of nodes. To encode a graph in Java, you would declare a class called graph that is composed of a set of nodes and a set of edges. Node would be a class that perhaps has a label such as name, and the edge is a pair of two nodes. In this case, the edge has directionality. We distinguish the from in two nodes. To express a graph representation of a molecule, we would encode the molecules as a list of atoms and a set of bonds. A list in Java means an ordered list. Each atom will have a specific index or position within this list. We have already defined the class atom as being 3 integers for expressing its number of protons, neutrons, and electrons. We then can express the bonds as being integer pairs referencing the position of the atom in question from the nodes list. For purposes of discussion, I'll simplify our representation of the molecule to just the list of characters in which we use the letter codes like C for carbon, O for oxygen, etc. to describe the atoms. Let's look at an example of the graph representing ethanol. I'll arbitrarily assign an index to each atom in the molecule starting with 0 and going from 9. There are 9 atoms, so there are 9 indices, and my list of atoms will have a size of 9. If I now list out the letter code for each atom, I construct the atom list. For each bond in the molecule, I'll express the indices that the bonds connect together. So, for example, the leftmost bond between the hydrogen labeled 0 and the carbon labeled 3 would be the bond 0, 3. Stereochemistry deals with the fact that two molecules can be identical in terms of the attachment of their atoms, but nevertheless different in three-dimensional shape. For biological molecules, this comes from the fact that carbon has 4 bonds, and when in the sp3 hybridization state, having 4 different things attached to the carbon atom, you can have that in 2 different configurations that are mirror images of each other. Because of this, many organic molecules are chiral, and their mirror images is a distinct molecule. Note that the representation I have provided for a molecule neglects stereochemistry. This could be easily remedied by introducing a list of booleans to represent each atom in the node list as being the R or S configuration. Though stereochemistry is important to accurately describing molecules, we will ignore it for the sake of simplicity for now.